Before we begin, please note that this presentation is for informational purposes only. I am not a licensed engineer or a legal professional. The information provided in this video does not constitute professional engineering, financial, or legal advice. Always consult with a qualified and licensed professional for your specific situation before making any decisions regarding your commercial property or HVAC systems. A business owner I know, let's call him Dave, sank his entire life savings into opening a beautiful 2-story boutique fitness studio. He had it all. Top-of-the-line equipment, charismatic instructors, a smoothie bar, everything was perfect. Except for one thing. The upstairs yoga studio with its floor-to-ceiling windows facing the afternoon sun became an unbearable sauna by 2 p.m., while the downstairs weight room felt like a meat locker. His members were constantly complaining. He had people canceling memberships because they were either sweating through a hot yoga class they didn't sign up for, or shivering while trying to lift weights. Dave's energy bills were astronomical because his single massive HVAC unit was running non-stop, fighting a war on 2 fronts and losing badly. He was bleeding money, losing customers, and his dream was turning into a nightmare. What was the culprit? It wasn't a faulty unit. It wasn't bad insulation. It was a problem that plagues tens of thousands of commercial buildings across the United States, and it's likely costing you money right now. It's called improper commercial zoning, or more accurately, a complete lack of it. This isn't just Dave's story. This is the story of the office manager dealing with thermostat wars between the sunny side of the building and the shady side. It's the story of the restaurant owner whose kitchen staff is roasting at 90 degrees, while diners in the front of the house are asking for blankets. It's the story of the warehouse manager paying to heat or cool thousands of square feet of unoccupied space. The Department of Energy estimates that heating and cooling accounts for nearly 40% of the energy used in commercial buildings. What they don't always tell you is that experts believe as much as half of that is pure waste, thrown away by inefficient systems that treat a complex building like a single empty box. That's why you're here. Over the next 10 parts, we are going to pull back the curtain on the world of commercial HVAC zoning. This isn't just for HVAC technicians. This is for business owners, property managers, and anyone who pays the utility bills for a commercial space. I'm going to give you the knowledge that most contractors assume you don't have. You will learn what zoning actually is, how to diagnose the problems in your own building, and you'll discover the specific questions you need to ask to ensure you get the right solution and not just the most expensive one. By the end of this series, you'll be equipped to slash your energy costs, eliminate comfort complaints, and take back control of your building's environment. So what is zoning? Forget the technical jargon for a moment. Think of it like this. You wouldn't try to control every light in your entire building with a single light switch, would you? It would be absurd. The conference room, the lobby, the bathrooms, the offices, they all have different needs at different times. You need individual control. Zoning is simply applying that same exact logic to your heating and air conditioning. It's the practice of dividing a building into distinct areas, or zones, that can be controlled independently by their own thermostat. This sounds simple, but it is the single most overlooked and misunderstood aspect of commercial HVAC. And the reason it's so critical in a commercial setting comes down to one concept: variable heat loads. Your home is relatively simple. The heat load is fairly consistent. But a commercial building is a dynamic living thing. Consider a standard office building. At 9 a.m., the east side of the building is getting blasted by the morning sun, what we call solar gain. The temperature on that side of the building is climbing rapidly. Meanwhile, the west side is still cool and shaded. At the same time, a team of 12 people files into a conference room for a meeting. Each one of those people is a little 98.6-degree heater. Add in their laptops, a projector, and suddenly that one room has a massive concentrated internal heat load. A single thermostat located in a hallway somewhere has absolutely no idea this is happening. It only knows the temperature where it's sitting, so it tells the giant rooftop unit to pump out cold air. That cold air blasts the already cool west side of the building, making those employees freeze and grab sweaters. It might barely make the east side comfortable, and it does almost nothing to cool down that packed conference room, which has now become an oven. This is the tyranny of the single zone system. It's a one-size-fits-all approach that fits absolutely no one. It creates a constant battle where one area is always too hot, and another is always too cold. Your HVAC unit is forced into a brutal cycle of overcooling and overheating, running constantly, driving up your energy bill, and putting immense wear and tear on incredibly expensive equipment. The problem gets even more complex when you have different uses under one roof. Think of a strip mall. A laundromat with dozens of dryers running is right next to a boutique clothing store, which is next to a small accounting office. They all have wildly different heating and cooling needs. A single shared HVAC system trying to service all three is doomed to fail. The laundromat will be a furnace, the clothing store will be an icebox, and the office will be, well, somewhere uncomfortably in between. This is the core reason we need to talk about zoning. It's not a luxury. It's a fundamental requirement for an efficient and comfortable commercial space. Getting it right means your system only delivers conditioned air where it's needed, when it's needed. The yoga studio gets the extra cooling it needs in the afternoon without turning the downstairs weight room into a freezer. The conference room gets a blast of cold air during the big meeting, and then the system backs off when everyone leaves. The sunny side of the building and the shady side of the building are treated as the separate environments they truly are. The result? First, your energy bills plummet. We're not talking about a few percentage points, we're talking about savings of 25 to 35% or even more. For a medium-sized commercial building, that can translate to tens of thousands of dollars a year. Second, comfort levels skyrocket. And a comfortable employee is a productive employee. A comfortable customer is a customer who stays longer and spends more money. The constant complaints, the thermostat battles, the productivity drain, they all disappear. Finally, the lifespan of your equipment is extended. Instead of running at full blast all day, your system can operate more intelligently and efficiently, reducing the strain on compressors, fans, and other critical components. But before you can even begin to think about the solutions, the VAV boxes, the dampers, the smart thermostats, you have to start with a proper diagnosis. You have to learn to see your building not as one big space, but as a collection of smaller, unique microclimates. You need to become a detective, identifying the sources of your building's specific heat loads and comfort challenges. And the first step in that investigation is to understand the fundamental type of building you're dealing with from an HVAC perspective. Because a sprawling single-story warehouse and a multi-story office building present dramatically different challenges. Understanding your building's zoning profile is the critical first step to reclaiming control, and it's where our journey begins. So what exactly is a zoning profile? It's not some complicated engineering term, it's a simple idea. It's the unique thermal personality of your building. Think of it like a fingerprint. No two are exactly alike. Creating this profile means stepping back and looking at your commercial space not as one big box, but as a collection of smaller, distinct environments, each with its own set of demands, its own rhythm, and its own challenges for your HVAC system. Most business owners think their heating and cooling problems are about the equipment itself. They think, my air conditioner just isn't powerful enough, or this furnace must be getting old. But more often than not, the hardware is fine. The real problem is a fundamental mismatch. It's like trying to run a complex software program on the wrong operating system. The system is fighting a battle it was never designed to win because it doesn't understand the territory. It's treating a diverse, dynamic environment as a single, static room. And that's a recipe for failure, frustration, and frankly, flushing money right down the drain. To truly understand your building's zoning profile, we need to break it down into three core pillars. Get these three right, and the path to an efficient, comfortable building becomes crystal clear. The first pillar is the architectural reality. This is the physical, unchangeable nature of your building. It's the brick and mortar, the glass and steel. Start by asking, what is the building's orientation? Which side gets blasted by the intense morning sun? And which side faces the long, hot afternoon exposure? A wall of east-facing windows creates a greenhouse effect at 9 a.m. that's completely different from the thermal load on the shaded north side of the building. We're talking about a massive, predictable influx of heat energy that your system has to fight every single day. Then consider the structure itself. Is it a sprawling single-story layout where the roof absorbs heat like a giant solar panel, radiating it down into the workspace all day long? Or is it a multi-story building where the laws of physics are your enemy, with heat naturally rising, making the top floors consistently warmer than the bottom ones? What about insulation? An older brick building with single-pane windows has a thermal profile that's a world away from a modern, well-insulated structure with high-performance glass. One leaks conditioned air like a sieve, while the other holds onto it tightly. Your HVAC system needs to know which kind of building it's living in. The second pillar, and this is a huge one, is occupancy dynamics. This is all about the people. Where do they go, when do they go there, and what are they doing? A standard office building might have a predictable rhythm. People arrive around 8, the population peaks midday, and then it empties out by 6. But even within that simple schedule, the dynamics are complex. A conference room might be empty and cold for 3 hours, then suddenly packed with 20 people for a meeting. Each of those people is a tiny 98.6-degree heater, also breathing out warm, humid air. That room's thermal demand just skyrocketed. But what about the individual offices that are now empty? An HVAC system that can't tell the difference will keep blasting cold air into those empty offices, while the conference room turns into a sauna. Now contrast that office with a restaurant. The occupancy is completely different. You have a massive peak during the lunch rush, a lull in the afternoon, and then another huge peak for dinner service. The dining room needs to be cool and comfortable for guests, but what about the kitchen? That brings us to our third pillar. The third pillar is equipment and process loads. This is the invisible heat that's being generated by everything but the people. In a modern commercial space, this is often the single biggest factor, and it's the one most often ignored. That restaurant kitchen we just mentioned? It's a thermal war zone. You have ovens, deep fryers, grills, and ranges all pumping out colossal amounts of heat in a concentrated area. Trying to cool that kitchen and the adjacent dining room with the same system is like trying to have a conversation with someone who's standing next to a jet engine. It's a losing proposition. But it's not just kitchens. Think about a typical office. You have a server room or an IT closet. Even a small one can be packed with equipment that runs 24/7, generating a steady, intense stream of heat. If that closet is on the same zone as the offices around it, the thermostat out in the hallway has no idea it exists. To keep that hallway at a comfortable 72 degrees, the air conditioner runs and runs, turning the surrounding offices into ice boxes. Meanwhile, the servers in the closet are slowly cooking themselves, shortening their lifespan and risking a catastrophic failure, all because the HVAC system is blind to their needs. Every piece of equipment, from the copiers and printers in an office, to the specialized diagnostic machines in a medical clinic, to the heavy manufacturing equipment on a factory floor, contributes to this process load. It's a constant and often significant source of heat that your HVAC system has to combat. Now here's where it all comes together. The architectural reality, the occupancy dynamics, and the equipment loads don't exist in a vacuum. They interact with each other in complex ways. The west-facing side of your building, Pillar 1, gets baked by the afternoon sun, which is also when your office, Pillar 2, is at its peak occupancy, and all the computers and printers, Pillar 3, have been running for hours. It's a perfect storm of heat gain. Meanwhile, the empty north-facing storage room on the other side of the building is cool and stable. The fundamental mistake, the original sin of most commercial HVAC design, is what we call the single zone trap. It's the decision to treat that entire complex building, with its sunny side and shady side, its packed conference rooms and empty offices, its hot kitchen and cool dining room, as one single space, controlled by one single thermostat. That single thermostat becomes the dictator of the entire building's climate. But where is it usually located? In a hallway, or in a manager's office? A place that represents the thermal reality of maybe 5% of the total building. So, the system reads the temperature in that one isolated spot and makes a decision for everyone and everything else. Let's go back to our medical clinic example. The thermostat is in the central hallway. The waiting room up front is a wall of glass facing south. It's filled with people all morning. It's hot. The interior exam rooms have no windows, but they have heat-generating diagnostic machines. They're stuffy and getting warm. The administrative offices in the back have no direct sun and only one person in each. They're perfectly comfortable, but the thermostat in the hallway is satisfied. It reads 73 degrees, so the air conditioning doesn't turn on. The patients in the waiting room are sweating. The expensive equipment in the exam rooms is overheating. The only people who are comfortable are the ones lucky enough to be near the thermostat. Eventually, the heat from the waiting room and exam rooms bleeds into the hallway. The thermostat finally kicks the AC on, and it runs and runs trying to cool down those hot spots. By the time the waiting room is finally tolerable, the administrative offices in the back are freezing. The employees back there have sweaters and space heaters at their desks in the middle of July. This is the single zone trap in action. It creates a building at war with itself. It's a constant, wasteful cycle of overcooling and undercooling. Your HVAC equipment is forced into a state of constant crisis management, running inefficiently, working far harder than it needs to. This is what causes sky-high energy bills. This is what causes premature wear and tear, leading to expensive repairs and replacements. And this is what leads to endless complaints from employees, tenants, and customers. You're paying to condition the air, and then your employees are paying for space heaters to fight that very same conditioning. It's absolute madness. But it's the default reality for millions of square feet of commercial space across the country. Understanding your building's unique profile, its architecture, its use patterns, and its equipment is the only way to escape this trap. It's about seeing your building not as a single entity, but as a community of different environments that deserve to be treated according to their own unique needs. Once you have this profile, you're no longer guessing. You have a roadmap. You have the data you need to make intelligent decisions. Now that we can see the problem with this one-size-fits-all approach, the question becomes, what's the solution? How do we take this profile and turn it into an action plan? How do we arm our HVAC system with the intelligence it needs to deliver the right amount of conditioning to the right place at the right time? The answer lies in the technology of zoning itself, a world of dampers, sensors, and intelligent controls designed to conquer this very problem. And exploring that hardware is our very next step. So what are the tools of this trade? What is the actual physical hardware that turns a dumb one-size-fits-all HVAC system into a smart responsive network? It really boils down to three core components, an elegant trinity of technology: the dampers, the thermostats and sensors, and the central control panel. Think of them as the hands, the eyes, and the brain of your zoning system. And we're going to start with the hands, the dampers. At its simplest, a damper is just a valve inside your ductwork. It's a plate or a series of plates that can rotate to either allow air to pass or block it off completely. It's the gatekeeper of airflow. In a non-zone system, you might have a few manual dampers, maybe with a little lever on the outside of the duct that an installer sets once and then forgets forever. But in a commercial zoning system, these are not passive, forgotten pieces of metal. They are active, automated, and absolutely critical. These automated dampers are controlled by small motors called actuators. When the system needs to change the airflow to a zone, it sends an electrical signal to the actuator, which then physically opens or closes the damper. It's the direct, physical action that makes zoning possible. But not all dampers are created equal. The two most common types you'll see are blade dampers and bypass dampers. Let's talk about blade dampers first. Imagine a rectangular duct. A blade damper inside could be a single, solid plate that pivots open and closed like a drawbridge. Or, more commonly in commercial applications, it'll be a series of smaller, interconnected plates like a set of Venetian blinds. These multi-blade dampers come in two main flavors: parallel and opposed. With parallel blades, all the little blinds move in the same direction, like they're waving at you. This design is great for quickly opening or closing a duct. It's more of an on or off switch. Opposed blade dampers, on the other hand, are more sophisticated. When they open, the adjacent blades move in opposite directions. One goes up, the next goes down. This creates a much more uniform, less turbulent airflow and allows for incredibly precise control over the volume of air passing through. It's not just on or off. It's 10% open, 45% open, 80% open. This is called modulation, and it's key to finely tuning the comfort level in a sensitive area like a conference room or a corner office. Now for the second type, the bypass damper. This one is the unsung hero of the system, the guardian of your HVAC unit's health. Think about it. What happens when your powerful commercial blower is running at full tilt, but 7 out of 10 zones have closed their dampers because they're already comfortable? All that air pressure has to go somewhere. If it doesn't, it builds up in the ductwork, creating what's called high static pressure. This can lead to noisy vents, strained fan motors, and can dramatically shorten the lifespan of your very expensive HVAC equipment. It's like putting your thumb over the end of a running garden hose. The pressure builds until something gives. The bypass damper is the system's safety valve. It's installed on a special duct that connects the main supply duct back to the return duct. When the control panel senses that static pressure is getting too high, it opens the bypass damper, allowing a portion of the conditioned air to loop directly back to the HVAC unit, safely relieving the pressure. It ensures the system is always breathing properly, no matter how many zones are calling for air. Without a properly installed and calibrated bypass damper, a zoning system is a ticking time bomb for your equipment. So we have the dampers, the hands, physically directing the flow of air. But how do they know when to open or close? They need instructions. And those instructions start with the eyes and ears of the system, the thermostats and sensors distributed throughout the building. Each zone, by definition, must have its own thermostat or, increasingly, a network of sensors. This is the fundamental principle. You cannot control the temperature in a zone if you are not measuring the temperature in that zone. Placing a single thermostat in a central hallway to control a 10-office building is like trying to drive a car by only looking in the rearview mirror. You're getting some information, but it's not the information you actually need to go forward. The thermostat in each zone acts as the local commander. It has one job: constantly compare the actual temperature in the room to the desired temperature, or the set point. When the room gets too warm, it sends a call for cooling signal. When it gets too cold, it sends a call for heat. It's the trigger. But modern commercial systems are often far more advanced than a simple wall thermostat. We're now in the age of intelligent sensors. These devices can do much more than just read temperature. They can measure humidity, which is a huge factor in perceived comfort. They can have occupancy sensors, using passive infrared or ultrasonic technology to detect if people are actually in the room. Why waste energy cooling an empty office? The system can automatically go into an energy-saving setback mode when nobody is there. Some advanced sensors even measure CO2 levels. As people breathe in a sealed room, CO2 levels rise. High CO2 can lead to drowsiness, headaches, and a loss of productivity, that classic stuffy conference room feeling. A smart zoning system can detect this and tell the central HVAC unit to bring in more fresh, outside air specifically to that zone, purging the stale air and keeping the occupants alert and productive. These sensors provide a rich, detailed picture of the environment in each and every zone, feeding a constant stream of data back to the brain of the operation. And that brings us to the third and most important piece of the puzzle: the zone control panel. If the dampers are the hands and the sensors are the eyes, the control panel is the central nervous system and the brilliant brain that makes it all work in harmony. This is typically a sophisticated circuit board, often hidden away in a utility closet near the HVAC unit. Every single zone thermostat and every single motorized damper is wired directly into this panel. It's the grand central station of information and commands. Here's how it orchestrates the entire symphony. The panel constantly listens to the signals coming from all the zone thermostats. Let's say the thermostats in Zone 1, the front offices, and Zone 3, the conference room, are both sending a call for cooling. The thermostat in Zone 2, the back warehouse, is satisfied and is sending no signal. The control panel receives these inputs and its logic kicks in. First, it aggregates the calls, sees that at least one zone needs cooling. So it sends a command to the main HVAC unit, telling it to turn on the air conditioning. Step 1 is complete. Cold air is now being produced. Next, it looks at the individual zones. It knows Zone 1 and Zone 3 need that cold air. So it sends a signal to the actuators on the dampers for Zone 1 and Zone 3, telling them to open. Simultaneously, it knows Zone 2 is already comfortable, so it ensures the damper for Zone 2 remains closed, preventing that part of the building from being overcooled and wasting energy. It also monitors the overall system pressure. If it detects that too many dampers are closed and the pressure is rising, it will modulate that all-important bypass damper to keep the system running smoothly and safely. It's a master conductor, interpreting the needs of each section of the orchestra and ensuring they all play together to create the perfect performance. A comfortable, efficient, and responsive building. This brain is what prevents conflicts, like one zone calling for heat while another calls for cooling. The panel's logic will prioritize or stage the operations, ensuring the system isn't fighting itself, a common and destructive problem in poorly designed systems. This combination, the brawn of the dampers, the senses of the thermostats, and the intelligence of the control panel, is what elevates an HVAC system from a blunt instrument into a precision tool. And understanding how these components are put together into specific, real-world configurations is the key to unlocking the perfect solution for any commercial space. So let's talk about those real-world configurations. Think of the components we just discussed, the thermostats, the dampers, the control panel, as ingredients. Now we're going to look at the recipes. These are the fundamental system designs, the blueprints that dictate how a building breathes. And just like in cooking, you start with the basics. The most basic, the most common, and frankly, the most primitive configuration is the single-zone constant volume system. The name says it all. One zone, one constant volume of air. You have one thermostat controlling one large air handler which conditions a single large space. This is the sledgehammer of the HVAC world. It's on or it's off. It's heating or it's cooling. There is no in-between. You see these systems everywhere, typically in buildings with simple needs. A small open-plan office, a standalone retail store, or a warehouse. The appeal is its simplicity. It's relatively cheap to install, the mechanics are straightforward, and there are fewer moving parts to break. The problem? It's incredibly stupid. It treats a complex building with diverse needs as one monolithic block. Imagine a small office with this system. The thermostat is centrally located in the main bullpen. But what about the corner office with floor-to-ceiling glass windows? On a sunny afternoon, that office becomes a greenhouse, baking the executive inside. Meanwhile, the server room, tucked away in a windowless closet, is pumping out heat constantly. And what about the employee sitting directly under a supply vent? They're living in a perpetual Arctic blast, wearing a parka in July. The single thermostat in the hallway has no idea about these microclimates. It only knows its own temperature. So it satisfies itself, leaving everyone else to suffer. This leads to the legendary office thermostat wars. A battle of passive-aggressive adjustments that solves nothing, because the system itself is the problem. It's a one-size-fits-all solution that, in reality, fits no one perfectly. It's a recipe for discomfort and staggering energy waste, because you're blasting conditioned air into spaces that might not even need it. So, what's the first logical step up from this? If one giant unit is causing problems, the knee-jerk solution is often to use several smaller, independent units. This is less a sophisticated zoning strategy and more of a brute force division of the problem. Instead of one massive rooftop unit trying to cool an entire building, you might install 3 smaller units, each with its own dedicated thermostat and ductwork, serving 3 different sections of the building. You see this approach in places like strip malls, where each retail tenant gets their own separate HVAC system. Or in a larger office building, the accounting department might be on one system, sales on another, and the executive suites on a third. On the surface, this seems like an improvement, and in some ways it is. You've broken the building down into larger zones. The accountants can have it a little cooler for their servers, while the sales floor can be a bit warmer. You also gain redundancy. If one unit goes down, you don't lose climate control for the entire building. But look closer, and you'll see this is still just a collection of single-zone systems. It's not true zoning, it's just multiplication. Each of those 3 systems is still a sledgehammer, just a smaller one. Within the accounting department, the person by the window is still fighting the person in the interior. You haven't solved the core issue of diverse needs within a single space. Furthermore, you've tripled your hardware. You now have 3 sets of compressors, fans, and filters to buy, install, and maintain. Your roof starts to look like a mechanical junkyard, and the energy waste is still immense. Each unit is either running at full capacity or it's off. There's no finesse, no ability to just send a little bit of cooling here or a little bit of heating there. It's an all-or-nothing proposition, just repeated 3 times over. It's a more expensive, more complex version of the same flawed idea. To find a smarter solution, engineers had to rethink the entire process. They needed to move from brute force to precision. This led to the creation of the first true zoning system, the constant volume multi-zone system. Now, this is a fascinating piece of engineering history, and though it's less common in new installations today, understanding it is crucial because it laid the groundwork for everything that came after. Here's the brilliant yet deeply flawed concept. You still have one large central air handler, usually on the roof or in a mechanical room. But this unit does something clever. It produces 2 separate streams of air simultaneously. One stream passes over a heating coil, creating a hot deck of air. The other stream passes over a cooling coil, creating a cold deck. These 2 decks of air, one hot and one cold, run in parallel ducts to a series of mixing boxes located near the zones they serve. Each zone has its own thermostat. When a zone's thermostat calls for cooling, it sends a signal to its assigned mixing box. Inside that box, a set of dampers adjusts to allow more air from the cold deck to enter the zone, while restricting air from the hot deck. If the zone needs heat, the opposite happens. The dampers shift to bring in more hot air and block the cold. If the zone needs a temperature somewhere in the middle, the dampers modulate to blend the perfect ratio of hot and cold air to satisfy the thermostat. This was a revolutionary leap forward. For the first time, a single centralized system could provide simultaneous heating and cooling to different parts of a building. The corner office getting baked by the sun could receive pure cold air, while the chilly interior conference room could receive warm air, all at the same time, from the same central unit. This system offered a level of granular control that was previously unimaginable. It was the first system that truly listened to the individual needs of different spaces. But it had a fatal flaw, an energy-guzzling, wallet-destroying, catastrophic flaw. Remember the name: constant volume multi-zone. The air handler runs at a constant full blast speed, all day long, and it's always producing both maximally hot air and maximally cold air, regardless of the actual demand. Think about what that means. On a mild spring day, the system is spending enormous amounts of energy to both heat and cool air, only to then immediately mix that air back together to create a mild temperature before sending it into the room. It's the energy equivalent of flooring the gas pedal and the brake at the same time. You're fighting yourself. You are paying to create two thermal extremes, then paying again in the form of wasted energy to destroy them through mixing. The inefficiency is breathtaking. While it solved the comfort problem with an elegant mechanical solution, it created an economic and environmental nightmare. These systems were brilliant in their ability to control temperature, but they were monsters of consumption. Facility managers would get utility bills that looked like phone numbers. The constant wear and tear on the system from running at full tilt meant higher maintenance costs. It was a classic case of solving one problem by creating another, arguably bigger one. The industry had created a system with surgical precision for comfort, but it wielded a financial sledgehammer. They had to find a better way. They needed a system that offered the same granular control without the apocalyptic energy bill. They needed to stop just mixing hot and cold, and start getting smarter about how much air they were moving in the first place. This realization, born from the spectacular failure of the constant volume multi-zone system, would directly lead to the single most important innovation in modern commercial HVAC, the variable air volume system. And so the stage was set. The industry had created a monster, a brute force solution that worked, but at an unbelievably wasteful cost. It was like using a sledgehammer to crack a nut. The constant volume multi-zone system was loud, inefficient, and fundamentally broken. Engineers knew there had to be a better way. The question wasn't if a revolution was coming, but when. The answer arrived in a concept so elegant, so profoundly simple, that it would permanently change the skyline of every city in the world. This was the dawn of the variable air volume system, or as it's known everywhere, VAV. The core idea of VAV is almost laughably obvious in retrospect. It's one of those inventions that makes you smack your forehead and say, "Why didn't we think of that sooner?" The engineers looked at the old system, the one that ran a giant fan at full blast 24/7, chilling all the air down to a frigid 55 degrees, and then used massive heaters to warm it back up again for most of the building. And they asked a simple question. What if, instead of fighting ourselves, we just gave each room the exact amount of cold air it actually needs? It was a complete paradigm shift. Let me put it this way. The old constant volume system was like driving your car with your foot slammed to the floor on the gas pedal all the time and controlling your speed by riding the brakes. You're generating maximum power and then immediately destroying most of it with friction and heat just to go the speed you want. It's insane. It's wasteful. And it's exactly what buildings were doing with their air. VAV was the invention of the accelerator pedal. It proposed that maybe, just maybe, it was smarter to give the engine just enough gas to go the desired speed. Instead of a constant volume of air at a variable temperature, the new system would provide a variable volume of air at a constant temperature. The air in the main duct would still be chilled to that efficient 55-degree set point. But the magic, the revolution, was in what happened next. The delivery system was no longer a network of dumb, wide-open gates. It became an intelligent, responsive network. And the hero of this new story, the piece of technology that made it all possible, is the VAV box. Think of a VAV box as a smart traffic cop for your air ducts. It's a relatively simple sheet metal box installed in the ductwork just before the air enters a specific zone, be it a single office, a conference room, or an entire wing of a floor. Inside this box are three critical components. First, there's a damper. This is basically a plate like a throttle valve in an engine that can pivot to open or close the airway. It's the gate that controls how much air gets through. Second, there's an actuator. This is a small, precise motor, a little robotic arm that physically moves the damper. And third, there's the brain, a controller that's connected to the room's thermostat. Here's how this beautiful symphony works in practice. Let's imagine a conference room at 9 a.m. It's empty, and the sun isn't hitting the windows yet. The thermostat reads a perfect 72 degrees. The brain in the VAV box says, "We're good here." And it tells the actuator to almost completely close the damper. Only a tiny minimum amount of air trickles into the room, just enough for basic ventilation. Now at 10 a.m., 15 people file in for a big meeting. Suddenly you have 15 human bodies, 15 laptops, and a projector all generating heat. The temperature in the room starts to climb. The thermostat senses this change. Maybe it hits 74 degrees. It sends an urgent signal to the VAV box's brain. The brain immediately commands the actuator, the little robot arm, to start opening the damper. A cool, refreshing stream of 55-degree air begins to pour into the room, much more than before. The system actively counteracts the heat being generated. As the room cools back down towards 72, the thermostat signals again, and the VAV box modulates the damper, throttling the air back just enough to maintain that perfect temperature. The meeting ends, everyone leaves, and the box closes the damper back down to its minimum position. It's dynamic. It's responsive. It's intelligent. It's only giving the zone the exact amount of cooling it needs, right when it needs it. No more, no less. There's no massive heater at the other end of the duct fighting a war against a torrent of freezing air. The waste is just gone. Now multiply this process by every single zone in the building. The accounting department, which is always cold, has its VAV box damper mostly closed. The sunny corner offices on the west side of the building have their dampers wide open in the afternoon. The lobby, with its doors constantly opening, has a VAV box that is constantly adjusting to the changing load. Every single zone is getting a custom-tailored amount of air, but this created a new fascinating problem. If all these little dampers all over the building are constantly opening and closing, what does that do to the system as a whole? Think of it like a plumbing system. If you have one massive pump running at full speed and 100 faucets, what happens when 90 of those faucets suddenly get turned off? The pressure in the pipes would skyrocket. You'd blow a gasket. The same thing was happening in the ductwork. When most of the VAV boxes closed down because the building was comfortable, the pressure created by the main air handler fan, which was still running at 100% like in the old days, would build up to enormous levels. The ducts would start to bulge. You'd hear whistling and roaring noises from the few vents that were still open, and the system would be under incredible strain. The initial clumsy solution was something called a dump bypass. They would literally just install a giant damper that would sense this high pressure and dump the excess cold air right back into the return duct before it ever reached the rooms. Which, if you think about it, is just another form of insane waste. You're paying a fortune to chill all this air just to throw it away. The real solution, the second key innovation that makes modern VAV systems possible, was the variable frequency drive, or VFD. The VFD is the VAV box's essential partner. It's the intelligent gas pedal for the giant fan motor back in the air handler. A VFD is an electronic controller that can change the speed of an electric motor by adjusting the frequency of the power going to it. Instead of the fan being either on or OFF, all or nothing, the VFD allows it to run at any speed from, say, 20% up to 100%. Now the system becomes a truly cohesive ecosystem. Pressure sensors are placed in the main ductwork. These sensors talk to the VFD. When VAV boxes all over the building start to close their dampers, the pressure in the duct begins to rise. The sensor detects this and tells the VFD, "Hey, we don't need this much push." The VFD then gracefully slows the main fan down. As rooms heat up and VAV boxes open, the pressure drops, and the sensor tells the VFD to ramp the fan speed back up. This is the masterpiece of modern HVAC. It's a system of perfect communication. The thermostats are the scouts on the ground, reporting the thermal conditions in each individual zone. The VAV boxes are the field commanders, adjusting the supply lines to their specific zone based on those reports. And the VFD is the general at headquarters, watching the overall pressure of the entire system and adjusting the speed of the main supply fan, the engine of the whole operation, to perfectly match the total real-time demand of the entire building. Not a single cubic foot of air is moved unnecessarily. Not a single watt of electricity is wasted spinning a fan faster than it needs to go. The impact was staggering. The energy savings weren't just a few percentage points. VAV systems slashed building energy consumption by 30, 40, even 50% or more compared to their predecessors. For building owners, this wasn't just an improvement. It was a financial miracle. The VAV system delivered on the ultimate trifecta: superior comfort, granular control, and drastically lower operating costs. It was the silver bullet the industry had been dreaming of. It was so effective, so logical, that it quickly became the undisputed standard for almost every new commercial office, hospital, school, and skyscraper built from the 1970s onward. Seemed perfect. A system that could think, that could respond, that saved a fortune and kept everyone comfortable. The war against waste had been won. But in engineering, as in life, there are no perfect solutions. There are only trade-offs. And in solving the massive energy problem of the constant volume multi-zone system, the VAV system had quietly created a set of new, more subtle, and in some ways more complex challenges. What happens, for instance, in a zone on a mild day when it doesn't need any cooling, but the people inside still need fresh air to breathe? The simple Vivi box wants to close its damper completely, potentially starving the room. The elegant simplicity of variable volume was about to run headfirst into the unyielding laws of ventilation and human health. This collision of needs created two immediate critical failures in the simple VAV system. The first was a violation of the laws of man, the second a violation of the laws of physics. The law of man is written in building codes, most notably ASHRAE Standard 62.1, the Bible of ventilation for acceptable indoor air quality. It dictates that occupied spaces must receive a minimum amount of outdoor air at all times. This isn't a suggestion. It's a requirement for health and safety. It's how we purge carbon dioxide, dilute contaminants like VOCs from carpets and furniture, and generally keep the air from becoming stale and suffocating. A simple Vivi box, in its quest to satisfy the thermostat, would happily choke off this vital lifeline of fresh air, closing its damper down to zero. Suddenly, your state-of-the-art, energy-efficient office could become a stuffy, CO2-filled hotbox that harms productivity and occupant well-being. The system was saving energy at the direct expense of the people it was designed to serve. The second failure, the one against the laws of physics, was a comfort disaster called dumping. The air coming from the central air handler is cold, typically around 55 degrees Fahrenheit. Cold air is denser and heavier than the warmer air in the room. When the VAV damper is wide open, this cold air shoots out of the diffuser with high velocity, mixing effectively with the room air before it ever reaches the occupants. This process is called induction. But what happens when the room is getting close to its set point and the VAV damper throttles down to, say, only 10% open? The volume of air is now tiny. It dribbles out of the diffuser with almost no velocity. Because it's so cold and dense, it doesn't mix. It simply falls like a chilly, invisible waterfall, straight down onto the unfortunate person sitting below. This creates a miserable draft, leading to endless complaints of being cold, even when the room's average temperature is perfect. The system was creating microclimates of misery. So, the engineering world faced a paradox. How do you provide a variable amount of cooling, while also guaranteeing a constant amount of fresh air, and avoiding cold air dumping? The answer was to give the dumb box a brain and a motor. This was the birth of the fan-powered VAV box, also known as a fan-powered terminal unit. And it came in two distinct flavors, series and parallel. Let's start with the series fan-powered box. Imagine the original VAV box, but now we place a small, quiet fan inside the box right after the main damper and before the air outlet to the room. The key here is the word series. It means the fan is in the main path, and all air delivered to the room must pass through it. And here's the brilliant part. This fan runs continuously whenever the zone is occupied. It never shuts off. Now, how does this solve our problems? Well, the box also has a secondary opening that sucks in air from the space above the ceiling, which we call the plenum. The plenum air is just return air from the room itself, so it's warm, typically around 75 to 80 degrees. So picture this, a corner office on a mild day. The room needs just a tiny bit of cooling. The main VAV damper, which receives the cold 55-degree air from the central unit, closes down to its minimum position, maybe 10 or 20% open. In the old system, this would cause dumping, but not here. The constant running series fan kicks into high gear. It pulls in that small stream of cold primary air and blends it with the large volume of warm plenum air that it's pulling through its secondary opening. The result? A full, constant volume of air is delivered to the room, but it's no longer a frigid 55 degrees. It might be 65 or 70 degrees, mild, comfortable, and delivered with enough velocity to mix properly. No dumping. And what about the fresh air problem? Solved. Because the central air handler is always providing a minimum amount of fresh outdoor air, and the series fan box is always moving air, that minimum ventilation is guaranteed to be delivered to the space. The fan ensures a constant circulation, preventing any stagnation. The series fan-powered box was a game-changer. It provided excellent comfort, guaranteed ventilation, and still allowed the central system to vary its output for energy savings. The main drawback? That little fan runs all day long, using a small but constant amount of electricity. For engineers and building owners, every watt counts, which led them to develop the second flavor, the parallel fan-powered box. The parallel box looks a bit different. The fan isn't in the main air path. Instead, it's mounted on the side like a bypass lane on a highway. This is why it's called parallel. During normal cooling operation, this box behaves exactly like the original simple VAV box. The side fan is completely off. The main damper modulates the flow of cold, 55-degree primary air to cool the room. It saves fan energy because the local fan isn't running. But wait, you're thinking, doesn't that bring back the original problems of dumping and no ventilation at low loads? Yes, it absolutely does. The parallel box only reveals its magic trick when the room gets too cold. Imagine the same corner office, but now the sun goes behind a cloud. The room no longer needs cooling. The thermostat is satisfied. The main VAV damper closes completely. In a simple VAV box, this is where the air goes stagnant. But in a parallel fan-powered box, this is when the system springs to life. The moment the main damper closes, the control sequence turns on the parallel fan. This fan starts pulling that warm, 80-degree air from the plenum and delivers it to the room to provide heating. It essentially turns the terminal unit into a plenum-powered heater. The parallel fan only runs when the zone requires heat. This design is often seen as more energy efficient because the fan only operates a fraction of the time compared to a series unit. It's an on-demand system. However, it reintroduces a potential comfort issue: air stratification. During those deadband periods when the room needs neither cooling nor heating, the main damper is closed and the parallel fan is off. This means there's no air being delivered to the room at all, which can sometimes lead to a feeling of stuffiness if it persists for too long. So now we have a choice: the series box, a workhorse that guarantees constant air motion and perfect mixing, at the cost of running a fan all day, and the parallel box, a more energy-frugal option that provides heating on demand but can create periods of stagnant air. But there's one last piece to this puzzle. What if the air in the plenum isn't warm enough? On a very cold winter day, the return air in the plenum might only be 72 degrees. Trying to heat a room with 72-degree air is like trying to put out a fire with a squirt gun. It's just not effective. To solve this, engineers added one final weapon to the arsenal of the fan-powered box: the reheat coil. This is a small electric heater or a coil of pipes with hot water flowing through it, placed at the discharge of the box. Now, when the parallel fan kicks on and pulls in plenum air, it can pass that air through the reheat coil to boost its temperature to 90 or 100 degrees before delivering it to the room. This provides powerful, effective heating. Similarly, a series box can use its reheat coil to warm up the mixed airstream when simple plenum heat isn't enough. We had finally done it. We'd created a terminal unit that could cool with variable amounts of primary air, that could provide constant ventilation, that could prevent dumping, and that could heat a space on demand using either free heat from the plenum or dedicated heat from a coil. We had given each individual zone its own miniature air handler, complete with a fan and a furnace. We had achieved the pinnacle of zone-level control, but in solving the problem of the individual room, we had inadvertently created a massive, energy-guzzling monster at the scale of the entire building. Because now you had a situation where on a sunny autumn day, the south side of the building was calling for maximum cooling, while the shaded north side of the same building was calling for maximum heating. The central air handler was churning out Arctic blast 55-degree air, sending it to every single box in the building, only for half of those boxes to immediately turn on their electric heaters to fight it. We were running the air conditioner and the heater in the same room at the same time. The sheer inefficiency was staggering, and it was about to spark the next great war in HVAC design. This internal conflict, this civil war inside the building's own mechanical systems, was untenable. Engineers called it simultaneous heating and cooling, and it was the dirty little secret of commercial real estate. On paper, the VAV system was a model of efficiency. In reality, it was a thermodynamic nightmare, a Rube Goldberg machine of waste. The core problem was the medium itself, air. To deliver cooling, you had to move massive volumes of cold air through giant ducts. But that same air, once it got to a room that was too cold, had to be wastefully reheated. It was like driving your car with one foot on the gas and one foot on the brake. For decades, this was just accepted as the cost of doing business, the price of close enough comfort. The industry was locked in a stalemate, trapped by the limitations of its own central plant philosophy. But a revolution was brewing, not in the sprawling office parks of America, but across the Pacific in Japan. There, where space is at a premium and energy costs are sky-high, engineers were asking a fundamentally different question. Instead of asking, how can we make our central system more efficient? They asked, what if we don't have a central system at all? What if, instead of a single massive air conditioner trying to be everything to everyone, you had a whole network of small intelligent units that could work together? And what if, instead of using bulky air ducts to move energy, you used something far more efficient? Something like refrigerant. The result was a technology that would eventually be known as variable refrigerant flow, or VRF. And it didn't just iterate on the old system. It completely changed the game. Imagine your building's HVAC system not as a single, powerful but clumsy giant, but as a colony of ants. Each ant is small, but they work together in a highly coordinated, incredibly efficient network. A VRF system works on a similar principle. You have one outdoor condenser unit, the brains of the operation, connected by small copper pipes to multiple indoor units, or fan coils, located in different zones. Each indoor unit can operate independently. It's the ultimate expression of zoning. But here's the stroke of genius, the part that truly solved the VV reheat war. The refrigerant doesn't just flow in one direction. The system is dynamic. Think of it like a thermal ride-sharing service. Let's say the big conference room on the south side of the building is baking in the afternoon sun. It has too much heat. The thermostat tells its local indoor unit, "I need cooling." That unit essentially hails a ride. It uses the refrigerant to absorb the heat from the conference room, cooling it down. Now, in an old system, that heat would just be dumped outside, completely wasted. But in a VRF system with heat recovery, that captured heat becomes a valuable commodity. The system asks, does anyone else in the building need this heat? And maybe on the north side of the building, there's a manager's office that's perpetually cold. Its thermostat has been calling for heat. The VRF system, the smart dispatcher, sees this. It directs the refrigerant, now carrying the heat from the conference room, over to the manager's office. The indoor unit there extracts the heat from the refrigerant, warming the room, and the now cool refrigerant cycles back to pick up more heat. This is the magic of heat recovery. It's not just preventing waste. It's actively recycling energy within the building. The very problem that plagued VAV systems, one zone being too hot while another is too cold, became the VRF system's greatest strength. It turned a thermodynamic conflict into a symbiotic relationship. It stopped the Civil War and turned the building into a cooperative thermal economy, where excess energy from one area is intelligently redistributed to another. No more simultaneous heating and cooling. No more fighting yourself. The energy savings were astronomical, often cutting consumption by 30, 40, even 50% compared to traditional systems. So if this technology was so revolutionary, why didn't it take over America overnight? The first commercial VRF systems were introduced by Daikin in Japan in 1982. Yet for almost 2 decades, they were virtually unheard of in the United States. The reasons are a classic case study in market inertia and cultural differences. The U.S. commercial construction market was, and to some extent still is, dominated by a handful of massive manufacturers who had built their empires on traditional rooftop units and chilled water systems. Their entire business model, from manufacturing and distribution to the training of technicians and engineers, was built around the VAV paradigm. They had little incentive to promote a disruptive technology that would cannibalize their existing product lines. Furthermore, American buildings were different. We had the space for huge mechanical rooms and the plenum space for massive ductwork. The compact, modular nature of VRF was a solution to a problem many U.S. builders didn't think they had. And then there was the cost. The initial, first cost of a VRF system was significantly higher than a standard VAV system. The components were more complex, and it required specialized design and installation knowledge. For developers focused on the lowest possible upfront construction cost, it was a non-starter. They were looking at the price tag, not the long-term total cost of ownership. But then in the early 2000s, the tide began to turn. 3 powerful forces converged to pry open the American market. First, energy prices began to soar. The wasteful but cheap model was no longer sustainable. Building owners and facility managers started looking at their utility bills with a magnifying glass, and the staggering inefficiency of VAV reheat became a glaring liability. Second, the green building movement exploded. Programs like LEED, or Leadership in Energy and Environmental Design, began rewarding buildings for their energy efficiency. Suddenly, a VRF system wasn't just an expense. It was an investment that could earn valuable certification points, increasing a building's prestige and rental value. And third, the culture of the workplace was changing. The demand for individual comfort and control skyrocketed. The open-plan office, with its diverse thermal needs, made the limitations of large, single-zone systems painfully obvious. Tenants were no longer willing to accept being too hot or too cold. They wanted control. VRF, with its inherent ability to provide granular room-by-room zoning, was the perfect answer. The showdown was on. VAV versus VRF. It was a battle of philosophies. Centralized power versus a distributed network. Brute force versus intelligence. VAV was the old way. Move massive amounts of air, cool all of it, and then use raw energy to reheat it where needed. It was simple, familiar, and relied on technology that every contractor understood. VRF was the new way. Move only the energy you need exactly where you need it. Instead of huge ducts, it used small, flexible refrigerant lines that could be easily snaked through existing buildings, making it ideal for historic retrofits. Instead of a single, lumbering giant, it was a nimble, responsive network. It was more complex, yes, but it offered a level of efficiency and personalized comfort that the old guard simply couldn't touch. The war against inefficiency, sparked by the wasteful reheat coils of the VAV system, had finally found its champion. VRF had solved the puzzle of providing customized comfort to dozens of different zones without cannibalizing its own energy. It was a monumental leap forward. But in solving one problem, it inadvertently highlighted another. VRF was brilliant at moving heat around, but what about the air itself? The system was primarily focused on recirculation, on conditioning the air already inside the building. But buildings and the people inside them need to breathe. They need a constant supply of fresh, clean, oxygen-rich air from the outside. And that crucial piece of the puzzle, the ventilation, was a challenge that the elegant, closed-loop world of VRF wasn't designed to handle on its own. A new alliance would be needed to create the truly perfect indoor environment. This new partner is known as a DOAS, a dedicated outdoor air system. And its arrival on the scene fundamentally changed the equation for high-performance buildings. To understand its genius, you first have to appreciate the problem it solves. Imagine asking that sophisticated VRF system, with its delicate, precisely calibrated indoor fan coils, to suddenly ingest a massive gulp of raw, untreated New Orleans air in August. That's air at 98 degrees with 95% humidity. It's thick, it's heavy, it's saturated with moisture. The small indoor units, which are designed to handle the relatively minor temperature and humidity changes within a room, would be instantly overwhelmed. Condensation would form everywhere, efficiency would plummet, and the system would be fighting a losing battle it was never designed to wage. Now imagine the opposite, trying to pull in -10-degree winter air from Minneapolis. It's bone-dry, frigid air that would cause a similar shock to the system, forcing it to work overtime just to bring that air up to a tolerable temperature before it could even begin to condition the room. This is the core dilemma. VRF systems are masters of recirculation and thermal management. They are like a world-class surgeon, making precise adjustments to the existing conditions within the body. They are not, however, designed to be the emergency room trauma team, dealing with the wild, unpredictable environment coming in through the front door. Asking them to do both is a recipe for failure. So, a new strategy was born, a strategy of specialization. The DOAS says to the VRF system, "You handle the inside. You be the surgeon. I'll be the gatekeeper. I will handle the outside world." A dedicated outdoor air system is exactly what its name implies. It is a separate standalone piece of equipment with one and only one job: to find, capture, treat, and deliver all the fresh outdoor air the building needs to be healthy and compliant with code. It is the building's respiratory system. The process is both brutal and elegant. First, the DOAS pulls in that raw outdoor air. It immediately passes through a series of high-grade filters, stripping out dust, pollen, pollution, and other contaminants. This is the first line of defense for indoor air quality. But the real magic happens next. The DOAS conditions this air before it ever enters the building's occupied spaces. If the air is hot and humid, the DOAS uses its own powerful cooling coils and dehumidification cycles to cool it down and wring out that excess moisture, delivering air that is cool and comfortably dry. If the outside air is frigid and dry, the DOAS heats it and, if necessary, humidifies it, bringing it to a neutral, comfortable state. Only after this full treatment is the fresh air ready. It's then ducted into the building, often through a separate, low-velocity ductwork system, and gently introduced into each zone. Now, when this preconditioned fresh air mixes with the air in the room, the local VRF indoor unit barely notices. It's not being hit with a thermal shock. It just sees a slight, manageable change in the room's condition, which it can easily and efficiently correct. The VRF system is now free to do what it does best: maintain the precise temperature in each zone with minimal energy. It's a perfect division of labor. The DOAS does the heavy lifting of ventilation, and the VRF does the fine-tuning of temperature control. One system is no longer compromising the other. Together, they create an environment that is simultaneously energy efficient, perfectly comfortable, and incredibly healthy. But the story of this alliance gets even better. The engineers who perfected this partnership looked at the process and saw one massive, lingering inefficiency. In order to bring fresh air in, you have to push stale air out. It's a constant exchange. So, on that cold Minneapolis day, your system is spending all this energy to heat up that -10-degree air. At the very same moment, it's taking the perfectly warm 70-degree air from inside the offices, air you just paid good money to heat, and dumping it straight outside. It's like boiling a pot of water on the stove, while leaving the refrigerator door wide open. You're fighting yourself. The same is true in the summer. You're exhausting cooled, dehumidified 72-degree air, while simultaneously spending a fortune to cool down that 98-degree air you're bringing in. For decades, this was just the cost of doing business, the unavoidable energy penalty for having a healthy, well-ventilated building. This is where the concept of energy recovery enters the picture, and it is one of the single most impactful technologies in modern HVAC. The most advanced DOAS units are equipped with what's called an energy recovery ventilator, or ERV. Inside this device is a remarkable piece of engineering, often an energy recovery wheel or a core made of a special porous material. It's designed to allow heat and humidity to transfer from one airstream to another, without ever letting the two streams of air physically mix. Here's how it works. The warm, stale exhaust air from inside the building is routed through one side of this energy recovery core on its way out. At the exact same time, the cold, fresh intake air is pulled through the other side of the core on its way in. As they pass each other, a thermodynamic miracle occurs. The heat from the outgoing warm air is absorbed by the core and instantly transferred to the incoming cold air. The stale air leaves the building much colder, and the fresh air enters the system much warmer. The ERV can recover up to 80% of the energy from the exhaust air. That means instead of the DOAS needing to heat air from -10 all the way to 70, it's now receiving pre-warmed air that might already be 45 or 50 degrees. The amount of energy required to do the rest of the job is slashed. The process works in reverse in the summer. The cool, dry exhaust air passes through the core, chilling it down. The hot, humid intake air then passes through, transferring its heat and some of its moisture into the core, which is then carried away by the exhaust stream. The fresh air entering the DOAS is now pre-cooled and pre-dehumidified, again for free. It is quite simply recycling energy. It's capturing the heating and cooling energy you've already paid for, and using it again and again before it can escape. This isn't a minor tweak, it's a fundamental game changer. Pairing a VRF system with a DOAS that has energy recovery is the modern gold standard for commercial HVAC. It decouples the ventilation load from the building's thermal load, allowing each system to operate at peak efficiency. You get the zonal temperature control of VRF, the guaranteed fresh air and health benefits of a dedicated ventilation system, and the astonishing energy savings of recycling your building's own thermal energy. This is how you build a truly high-performance building. Not with one single magic bullet technology, but with a symphony of specialized systems, each a master of its craft, all working together. But having the world's best orchestra is useless without a conductor. How do you control and integrate these sophisticated systems to ensure they're working in perfect harmony and not against each other? That conductor has a name, and in the world of commercial buildings it's called a Building Automation System, or BAS. You might also hear it called a Building Management System, or BMS. For our purposes, they're the same thing: the brain, the central nervous system of your entire facility. This isn't just a fancy wall-mounted thermostat. Comparing a BAS to a thermostat is like comparing an F-22 Raptor to a paper airplane. They both technically fly, but they exist in entirely different universes of capability. The BAS is the invisible maestro that ensures the 100-ton chiller on the roof, the VAV box above your desk, the lighting in the hallway, and even the security system at the front door are not just working but are working together as a single cohesive entity. It's the digital ghost in the machine, constantly monitoring, adjusting, and optimizing every critical function of your building, 24 hours a day, 7 days a week, without ever taking a coffee break. So what does this digital conductor actually do? Its power can be broken down into a few core, game-changing functions. First, and most fundamentally, is centralized control. Imagine you're the facility manager of a 20-story office building without a modern BAS. A hot call comes in from the 17th floor, legal department. A cold call comes from the 3rd floor, accounting. To even begin diagnosing the problem, you're physically running around the building. You're in a mechanical closet on the 17th floor checking a local controller. Then you're down in the basement checking chiller pressures. Then you're back in your office trying to pull up the separate software for the lighting controls to see if that's interfering. It's an exhausting, inefficient, and wildly expensive game of whack-a-mole. Now, picture the same scenario with a state-of-the-art building automation system. That same facility manager sits down at their desk, opens a single piece of software, and sees a graphical representation of the entire 20-story building. They can see every floor, every zone, every piece of equipment in real time. They click on the 17th floor. They can see the exact temperature in the complaining zone, the position of the damper, the airflow in cubic feet per minute, and the temperature of the air being supplied. They can see the history, the trend logs, and the set points. In seconds, not hours, they can diagnose the problem and often fix it remotely with a click of a mouse. This is what we call the single pane of glass approach. It brings every disparate system, HVAC, lighting, access control, security cameras, into one unified command center. The power and efficiency gained from this alone is monumental. But centralized control is just the beginning. The second, and for many business owners, the most important function of a BAS is energy management. Commercial buildings are notoriously energy-hungry beasts. In the United States, they account for nearly 40% of all energy consumption. A significant chunk of that is waste. Lights left on in empty rooms, air conditioning blasting in unoccupied wings of a building over a holiday weekend. A BAS is the ultimate weapon against this waste. It goes far beyond simple timers. A sophisticated BAS integrates with scheduling software. It knows the company calendar. It knows that this Friday is a federal holiday, and that 95% of the building will be empty. So instead of running the systems as normal, it automatically puts the entire building into a deep unoccupied mode, maintaining just enough conditioning to protect the assets inside, but saving tens of thousands of dollars in energy costs for that one day alone. It can implement complex strategies like optimum start-stop. It knows it takes 2 hours to cool the west side of the building on a hot July morning. So, instead of just turning on at 6 a.m. every day, it looks at the weather forecast. It sees tomorrow will be cooler, so it waits until 7:15 a.m. to start the chillers, saving over an hour of massive energy draw. It does this every single day, compounding the savings. Gets even smarter. Through occupancy sensors or even CO2 sensors, the BAS knows in real time which spaces are being used. That giant conference room that's only used for 3 hours on a Tuesday? The BAS won't waste a single kilowatt cooling it to 70 degrees for the other 37 hours of the work week. It waits until it senses people have entered, and then brings the system online for that zone. This is the very definition of smart zoning, executed perfectly and automatically. It can even participate in demand response programs from the utility company. When the city's power grid is under extreme stress on a 105-degree day, the utility might charge astronomical prices for electricity during peak hours. The BAS knows this. It can automatically and subtly raise the temperature set points by a degree or two across the building, dim the non-essential lights by 10%, and pre-cool the building in the morning when energy is cheap, allowing it to coast through that peak price window. This strategy alone can save a large facility hundreds of thousands of dollars a year. The third critical function is one that prevents disasters: fault detection and diagnostics, or FDD. This is perhaps the most underrated and powerful feature of a modern BAS. In the old world, you found out a piece of equipment was broken when it actually broke. The air conditioning dies in the middle of a heat wave, a critical fan motor seizes up, and suddenly you have an emergency on your hands. Productivity plummets, tenants are furious, and you're paying exorbitant emergency repair fees. FDD changes the entire paradigm from reactive to proactive. The BAS is constantly monitoring thousands of data points from every piece of equipment. It's watching pressures, temperatures, valve positions, fan speeds, and vibration levels. It doesn't just know the fan is running. It knows how it's running. It uses sophisticated algorithms to learn the normal operating parameters of every component. And the moment something starts to deviate from that baseline, it raises a flag. It's the check engine light for your entire building, but infinitely more intelligent. It won't just tell you there's a problem. It will tell you what the problem is. You get an alert that says, "Warning, The primary chilled water pump's motor is drawing 12% more amperage than baseline under similar load conditions. Bearing vibration has increased by 8%. Recommend inspection and lubrication within 7 days to prevent catastrophic failure. This is not science fiction, this is happening in buildings right now. It allows you to schedule maintenance on your terms, during off hours, before a failure ever occurs. It transforms your maintenance budget from a source of emergency firefighting to a predictable, manageable operating expense. Finally, the BAS is a data goldmine. It logs everything. Every temperature fluctuation, every change in occupancy, every kilowatt of energy used. This historical data is invaluable. It allows building owners and managers to see patterns, to identify areas of inefficiency, and to make incredibly informed decisions about future upgrades. Should we invest in a new chiller? Or would window tinting on the south side of the building give us a better return on investment? The data from the BAS can answer that question with startling accuracy. It removes the guesswork from managing a multi-million-dollar asset. So the building automation system is the conductor that makes the orchestra play in tune. It's the central command that provides control, the financial wizard that slashes energy costs, the vigilant guardian that predicts and prevents failures, and the historian that provides the data to make smarter decisions tomorrow. It is the single most critical element in unlocking the true potential of a commercial HVAC zoning strategy. Without it, you just have a collection of expensive parts. With it, you have a living, breathing, intelligent building that works for you, not against you. We've assembled our orchestra, we've defined our musical sections through zoning, and we've put the conductor on the podium with the building automation system. The entire symphony is ready to play. But technology never stands still. The performance we're getting today is incredible, but what does the concert of the future sound like? What happens when this brain, this conductor, starts not just following the sheet music but composing its own? The answer is that the conductor stops being a conductor at all. It becomes a composer. And its instrument isn't just the building. It's the flow of time itself. We are on the cusp of the next great leap in commercial HVAC. The move from reactive systems to predictive, artificially intelligent environments. The brain of the system is no longer just following rules we gave it. It's learning. It's anticipating. Thinking. Imagine a system that isn't just connected to the thermostat on the wall, but to the entire digital ecosystem of your business and the world outside. It reads the weather forecast, not just for today, but for the next 3 days. It knows a heat wave is coming on Wednesday, so it begins subtly pre-cooling the thermal mass of the building, the concrete, the steel, on Tuesday night when electricity rates are at their lowest. By the time your employees arrive Wednesday morning, the building is already a cool reservoir, ready to absorb the day's heat without the system having to blast on at full power during peak, expensive hours. But it goes deeper. This AI conductor syncs with your company's shared calendar. It sees that the main conference room, Zone 7, is booked for a 20-person board meeting from 2 p.m. to 4 p.m. A traditional zone system would wait until 20 bodies file in, raising the temperature before kicking on the AC. The intelligent system, however, begins conditioning Zone 7 at 1:45 p.m., ensuring the room is perfectly comfortable the moment the meeting starts. It also knows that after 4 p.m., the room is empty, so it can ramp down service immediately, not waiting for a sensor to eventually notice the lack of motion. It doesn't react to the present. It prepares for the future. This isn't science fiction. This is the power of machine learning applied to building science. The system learns the unique thermal dynamics of your specific building. It knows that the east-facing offices get slammed with sun until 11 a.m. and require more cooling, while the west-facing side needs the opposite in the afternoon. It learns the occupancy patterns not just by room but by the day of the week. It knows that on Fridays in the summer, half the office leaves by 3 p.m., and it adjusts its entire strategy accordingly, saving a fortune in energy without a single person noticing a change in comfort. And we can push this even further, into the realm of hyper-personalization. The future isn't just about zoning for a room, it's about zoning for the individual. Through apps on our phones or smart wearables, the building could know your personal comfort preferences. As you walk from your desk to a collaboration space, the system makes micro-adjustments to airflow and temperature in your immediate vicinity. The person who is always cold gets a slightly warmer stream of air, while the person next to them who runs hot gets a cooler one. We're moving from building-wide control to room-wide control to person-wide control. This isn't just about comfort, it's about productivity. Study after study shows that when people are in their optimal thermal environment, their cognitive function, creativity, and overall well-being skyrocket. Now, what about when something goes wrong? The old way was simple. The system breaks, the building gets hot, people complain, and you make an expensive emergency call. The new way is entirely different. This intelligent composer is also its own physician. It's constantly listening to the symphony of its own machinery. It monitors the vibration signature of a fan motor, the amperage draw of a compressor, the pressure differential across an air filter. The AI knows the baseline, the perfect, healthy rhythm of the system. And when it detects a tiny, almost imperceptible change, a slight increase in vibration, a minuscule drop in pressure, it recognizes it as a symptom. It knows that this specific fan motor is 90% likely to fail in the next 300 operating hours. So instead of a catastrophic failure during a heat wave, the system sends an alert to the facility manager. It says, "The fan motor in air handler 3 is showing early signs of bearing wear. I recommend scheduling a replacement during the next 2 weeks. I have already cross-referenced the part number and found 3 local suppliers with it in stock." The breakdown is averted. The emergency is prevented. The building doesn't just react. It heals itself proactively. This shifts maintenance from a costly reactive fire drill to a predictable, planned and budgeted activity. But the most profound shift, the true crescendo of this entire composition, is when the building stops being an island. Right now, we think of buildings as individual consumers of energy. They plug into the grid and they take what they need. The smart, predictively zoned building of the future becomes a team player. It becomes an active, symbiotic partner with the electrical grid itself. This is a concept called demand response. The building's AI is in constant communication with the utility company. When the grid is under heavy strain, say on the hottest day of the year when everyone's AC is running, the utility can send out a signal. Instead of building a new multi-billion-dollar power plant, the utility can ask a network of smart buildings to temporarily reduce their consumption by 10 or 15%. Our building's AI receives this request. Because it has already been pre-cooling and has a deep understanding of its own thermal load, it can intelligently shed load without sacrificing occupant comfort. It might slightly raise the temperature by 1 degree, or reduce fan speeds in unoccupied zones. In return for being a good grid citizen, the building owner receives significant financial incentives and rebates from the utility. The building is no longer just a cost center. It's a potential revenue generator, helping to stabilize the entire energy infrastructure for the community. So where does this leave us? We've journeyed from the simple, clumsy idea of a single thermostat for an entire building to a world where our environment anticipates our needs, diagnoses its own illnesses, and collaborates with the world around it. We've seen how zoning evolved from a luxury of comfort into an absolute necessity for efficiency and control. We've understood that the true power lies not in the dampers or the diffusers, but in the intelligence that conducts them. Commercial zoning is not just an HVAC strategy. It is the very foundation of the modern high-performance building. It is the key that unlocks unprecedented energy savings, optimal human productivity, and a sustainable future. The questions you ask are no longer just, is it on or off? Or is this room cool enough? The questions you should be asking now are, is my building smart enough to prepare for tomorrow's weather? Is it intelligent enough to support my team's unique workflow? Is it a good enough citizen to help power our shared future? Because the buildings we create are more than just steel and glass. They are the ecosystems where we spend our lives, where we innovate, collaborate, and create. And by giving these ecosystems a brain, a smart, adaptive, and predictive zoning system, we're not just controlling the temperature. We are composing the perfect environment for human potential to flourish.